Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to describe the relationship between work and kinetic energy. So what we're looking at, right, imagine we've got this object, right here, and it has an initial velocity vector to the right. And I'm just going to make this a one-dimensional example, although this applies in 3D, no problem at all. Right, and imagine that we observe that the object speeds up. So the motion diagram would look something like this. We'd have that first delta x, right, and then the second delta x, and so forth. And the delta x is getting larger and larger and larger until we have a new v final. So there must be a force acting on that object to the right. So in the second picture here, we're going to imagine here we have this force, and here's our object. Now, if we apply Newton's second law to that, right, which says, all right, net force equals mass times acceleration. And we play around with this a little bit, all right? So what we're going to do is we're going to calculate the net work done on the object, right? So let's just imagine that this moves a distance d here. If we take this equation here, we multiply both sides by d, we get that the net work times distance equals mass times acceleration times distance. Now this is now the net work done. Now we're going to play around with the right hand side, and I'm going to do this in an algebraic sense here. So acceleration can be written change in velocity over change in time. And if we group these two things together here, this distance divided by time is the average velocity. So this is equal to m delta v times v bar here, where v bar is the average. So now we got that our net work is equal to m, and we're just going to rewrite this stuff a little bit. V final minus v initial, that's how we can write this. And then the average velocity we can write as v final plus v initial over 2. And if we go ahead and mess around with this, multiply this out, we get 1/2 m v final squared minus 1/2 m v initial squared. Right? This is a really important relationship in physics right here. Right? These terms 1/2 mv squared, these are called kinetic energies. And I like to define kinetic energy, right? Kinetic energy is defined as energy due to motion. Now, there's a little bit of a circular thing happening right now. We've not actually talked about what energy is, so I'm going to go ahead and define that right here. Okay. Energy is defined as the ability to do work. Now, kinetic energy is an object's ability to do work based on its motion. So, for example, when a car is moving along reasonably fast, it has a pretty reasonable kinetic energy, and that gives it the ability to apply force on something and move it, basically. Right? So, energy is the ability to do work. Kinetic energy is energy due to motion. Now, I'm going to go ahead and talk about potential energy in another video. I do want to point this out, though, that this equation right here, let's write it like this. If we put this term on the left, this says the initial kinetic energy of a system here, because this is 1/2 mv initial squared. So if I want, I could call that KE1 or KE initial. And if we move it onto the left, it would be positive. Plus the work done on the system is equal to my new or my final kinetic energy. So this is part of what's called the work energy theorem, and what we're going to do is talk about how to expand it to use potential energies very, very soon. But you'll notice that work is the term that changes your energy. You know, whatever energy you start with, plus any work that you add, yields your new kinetic energy. So probably enough for this video. I hope that this has described the relationship between work and kinetic energy for you. Have a great day.